If you've got your A-level chemistry exams coming up, you've got to make sure that you're not just revising the pH titration curve shape as a general outline. You've got to know a little bit more about it. We need to know things like the equivalence point and how to select an indicator to make it suitable for a titration. And so in this tutorial, I'm going to go through a triple threat of information to make sure that you're as prepared as possible going into the A-level exams. First off, I'm going to take you through the theory of what the shape of the curve is representing, why there is a vertical section, and how we know those before and after pH values. Next up, I'm going to take you through an exam question, probably the most robust one I've ever seen relating to pH curves, so make sure you stay tuned for that. And finally, I'm going to take you through something that's very rarely found in textbooks, but is quite a unique feature when we have a strong acid, strong base titration curve compared to a weak acid, strong base titration curve. You'll notice if you look these up, they start with their shapes in a slightly different way. And so I'm going to be taking you through the theory that surrounds that and linking it to another part of your A-level for that big potential crossover question. All right then everybody, it's time to talk about the theory surrounding the pH titration curves. So looking at a lab scenario setup for these and how we know the different pH values and what the different sections of the curve mean when we're looking at a theory or maybe perhaps even towards exam questions. Here what we've got is a pretty familiar scenario for a titration. We have a solution in a beerette being added to another solution, which this time is in a beaker, just so I can fit the pH meter in. The neck on a conical flask that we would conventionally see here is quite narrow, and so I'm using a beaker here instead, as it creates that little bit of wiggle room just there. Either way, the scenario is the same. One solution in a beerette, one solution below it, it's a known amount in a vessel, either a conical flask or in this scenario, a beaker. And I'm going to be going with sodium hydroxide, a strong base, being added to hydrochloric acid, a strong acid. If I was to flip these two around and do this the other way, then this curve over here would be the same shape, just inverted. And so we would see it start off, go down through the vertical section here and finish off over here instead. So do be mindful that the reason that I've got this low start point and the high end point up here is because of the way around my two solutions are in the titration apparatus setup. So let's go through the features of the curve and talk about all the parts you're expected to know ahead of the examination. First off, the starting point. Now the starting point is actually the pH of the reagent in the conical flask. Now in my scenario here, I'm using 0.1 mole per decimeter cubed HCl. And so because that's a strong acid, all I need to do is negative log that value, and that's going to get me the pH. And so I've chose to start my pH here at 1 in line with the calculation. Next up, you'll notice the graph has this vertical section to it, and the vertical section, if you consider the x-axis down here being volume, shows the curve has a very sharp pH change over a very small volume. We're talking drops here. The vertical section here is approximately 8 pH units. I like the boundary here of 3 to 11, but it will obviously be varied depending on what acid and what alkali you're using here. This titration, though, is between a strong acid and a strong base, and generally speaking, we do need to be able to make some assumptions about where the limits of this vertical section are going to be, so we'd be able to suggest a sketch of this in the exam. I'll give you more information on the different scenarios you could be presented with that shortly. The midsection here on the vertical section of the curve is called the equivalence point. Now, the equivalence point, as you can see on screen, is the point in a titration where all the acid or base from the start, which was in the conical flask, in my scenario, of course, it was an acid, has been reacted fully with the added acid or base from the beerette. Of course, I added a base, it was sodium hydroxide. The equivalence point is the midpoint on the vertical section of the curve. Now, for this particular titration, the midpoint is 7. But that isn't always the case. So please don't assume that the equivalence point is always going to be 7. It varies if we're using weak acid or weak bases inside our setup. You also need to avoid any language relating to the neutralization point. That's typically not a phrase that actually gets used inside these pH titration curves, as it's a bit misleading. The neutralization point, if you throw that out there, makes it sound like that every titration has got this midpoint on the vertical section which is equivalent to 7, and that's not the case at all. So please try and avoid the use of that term. We should be using equivalence point instead. Now over here we've got the final pH value, and the final pH value is found by calculating the excess moles of the reagent from the burette present. This is converting this then into a concentration and then using this in an appropriate equation to calculate pH. In this example, after 50 centimeters cubed of the sodium hydroxide is added, the pH actually comes out as 12.52. Now, if you're a bit curious on what that calculation would look like, there's an exam question coming up in just a moment, which takes you through this exact situation. Although it's not 50 centimeters cubed being added, it's 45. But if you just stay tuned for that, I'll take you through the full calculation and what you need to be able to do for that in an exam. I did mention before that these vertical sections here have a certain range which can be estimated depending on what reagents we've got in our burette and our conical flask. We've got the different 4 scenarios here you could be presented with in an exam. The different combinations here are strong acid, strong base, weak acid, strong base, strong acid, weak base, and weak acid, weak base. The weak acid, weak base one is a bit weak. It's not a great scenario. You don't really end up with a vertical section at all. You end up with this little quiver just in the middle of things. But the others have got something more significant to chat about. The vertical section here, if you look at the broadest possible one, is between 3 and 11. And then the others kind of fit in and around this. And so what we've got for the strong acid, strong base is the 3 to 11 I discussed before, with an equivalence point of 7, which is the middle section of that vertical point. What we've also got then is weak acid, strong base. Now I estimate here that this would be about 7 to 11, and of course these are estimations. Now the equivalence point here, because it can't be the 7 value anymore, because it has to be the midpoint of the vertical section, and we can see the vertical section is starting at around 7, it's got to be above 7, so it's got to be a greater than 7 value. It still needs to be at least 3 pH units as well in most mark schemes, and so that's why I go for this range of 7 to 11. The strong acid weak base, well, again here you can see that I can't have an equivalence point anymore of 7 because my vertical section of the curve appears to be going from 3 to 7 in this scenario. So the midpoint here of that vertical section is going to be less than 7 this time. Hopefully you can see why now I'm not using the term neutralization point. The weak acid, weak base one, I suppose the equivalence point would be about 7 here, but that vertical section is so hard to actually even observe that it's difficult to present the weak acid, weak base as a serious scenario. What other significance have we got about this vertical section of the curve? Well, we need this vertical section of the curve to help us choose a suitable indicator for the titration. The indicators need to have a pH range which sits within the vertical section of the curve so it can be used to identify the equivalence point. Phenolphthalein has got a pH range of about 8.3 to 10. Now that range sits perfectly inside the vertical section of this curve, and so that makes phenolphthalein a suitable choice of indicator for the titration. Generally speaking, the broader the vertical section is, the more choices you've got when it comes to the choice of indicator. The phenolphthalein would not have been a very good choice of indicator for the strong acid weak base titration that we looked at on the previous slide, because that vertical section actually was limited to 3 to 7 as a pH range. And so that means that the change point here, so the end point of the titration, which would be observed when the indicator changes its colour, would not be seen at that vertical section. And so we would completely bypass the equivalence point altogether. The big goal here is we want the pH range to help us identify the equivalence point. We want the pH range of the indicator where it changes colour to help us find that midsection on the vertical section of the curve. The next thing we need to look at then is moving into the exam questions. And so stay tuned now and I'll take you through a really robust example of a question that has come up before using lots of different types of calculation and asking you to sketch the shape of a pH curve. Here we have an exam question which is from the OCR A specification. This was from paper 1 in 2019. And of course, as you can see on screen, this was question 20. At the start of this question, we're given this table just here, which contains 3 different weak acids. The very first thing I noticed here is, I have no idea why other than maybe to hide it, but they've written this one, which is for iodic 5 acid, as 1.78 times 10 to the power of -1. Okay, that is 0.178. So it is a bit excessive maybe to put this here, but I suppose it's in keeping then with the rest of the data. What I will say, therefore, looking at this number, that is a very high value for a Ka. Most Ka values look like these two just here. That's a really high Ka value, and that suggests that that weak acid is actually dissociating quite a lot. That doesn't seem very partial at all. And so we will be having a look at that and how it comes up later in this question, as it is significant. We start off, however, by being asked to calculate the pH of a weak acid, and it's a pure weak acid sample, so I can use this a rearrangement, so just here, of the Ka expression. And so this takes into account my approximations, and it's A-OK to make sure that I don't need to start looking in here of where have I put the A-, because for this we know that the H plus and the conjugate base concentration, which would have been the A-, which is the C2H5COO negative, they would have the same concentration, which is where this square root has come from. If you're looking at this and thinking to yourself, I have never seen this before in my life, then there's a link in the video description to all the different types of pH calculation you can be presented with in an exam scenario for A-level chemistry, and you might want to check out that and go to the weak acid section. Here, once I've got my H plus ion concentration from this use of the Ka expression rearrangement, my pH comes out as 2.98. Next up, it's a bit of a weird question, and it uses some language from our pH titration curves. A student adds a total of 45 centimeters cubed of the 0.1 mole per decimeter cubed sodium hydroxide to 25 centimeters cubed of the weak acid. And now that's the same weak acid we were just looking at before up here. So it's this one up there. Show by calculation that 20 centimeters cubed of the sodium hydroxide is required to reach the end point. Now remember, the end point here is when enough of the burette reagent has been added to fully react the reagent in the conical flask. Try and ditch this idea of end point being perfectly neutral. That's not necessarily the case. So what we've got here is, for my calculation, I just need to show that they've got the same mole value. Based on this description here, when enough burette reagent has been added to fully react with the reagent in the conical flask, I'm trying to demonstrate that they've got the same moles. And so we're looking at these mole values being equivalent to each other, and we're making sure that these two have fully reacted, and that's our good description of the end point. Next up, we've been asked to calculate the pH of the final solution here. Now, this is the resulting solution after 45 centimeters cubed of sodium hydroxide is added to the 25 centimeters cubed of the weak acid. And you can see here I've got all my stages going down, and this I mentioned in the slides that were before this section of the video. How do we know what the final pH solution is going to be when we have this kind of scenario of a pH titration curve in an exam? Well, what I'm going to do first is figure out the moles of each of them at the start. So I can see here I've got my 0.002 mole of the weak acid, and I've got my 0.0045 mole of the sodium hydroxide. Here, I've not rounded up to two significant figures. I've just got trailing zeros after these numbers, so I've not rounded up. Please don't assume I'm encouraging you here to round up to 2 sig fig. It's just there's trailing zeros after this point, which is usually fine in exams. It wouldn't be fine if they said give my answer to a certain number of sig fig down here. Of course, they've asked for decimal places, so just be careful. It is okay, however, in my working out here because it is trailing zeros. What I do now is I try and figure out how much hydroxide is left unreacted, how much is in excess, it says in mark schemes, but I prefer the term unreacted. And what I do here is I work out the moles between the two. This is essentially a bit starty-offy as like a buffer calculation, but then it takes this turn here where the alkali is now the one in excess. Normally we get the weak acid for a buffer calculation, don't we? But we've got a slightly different scenario here where the alkali is now in excess by 0.0025 mole. Now what I need to do is turn this into a concentration of OH-, and I do so by doing the unreacted moles divided by the new volume of the final solution, which is not 45, it's 70, so that's the 25 and the 45 being added together. That gives me a hydroxide ion concentration of 0.0357 just there. Now, once I've got this OH- ion concentration, I use this rearrangement of the Kw expression at 298 Kelvin to help me find the H+ ion concentration. And again, if you're not familiar with this rearrangement, check out that pH calculation video in the description down below. So the H plus ion concentration here equals the Kw value from the data sheet of 1 times 10 to the power of negative 14 divided by the concentration of the hydroxide that we just calculated up here. That gives me an H plus ion concentration of 2.8, what would be 2.80 times 10 to the power of negative 13, and it gives me a pH of 12.55. You were asked to give your answer to 2 decimal places. We then move to this section here, which is the pH titration curve. Now, there's loads going on here. I'm going to take you through it. But it does say on the axis below, sketch a pH curve for the pH changes during the addition of the 45 centimeters cubed of the sodium hydroxide to the weak acid, so that would be the propanoic acid that was inside the conical flask. Now, there are some points here I've written on in pink that you need to be aware of when we're estimating and making decisions as well, using our prior calculations on where we need to place certain sections of our curve. I'm going to start off down here. So how did I know to start off at a pH of 3? Well, that was the pH of the solution in the conical flask that we did in part A of the question, just the propanoic acid all by itself. It was actually 2.98, and so I'm starting off my pH value here of 3. As I progress through the titration, I am of course going to get this vertical section here. So how did I know where to place the vertical section? Well, I needed to place it at the 20 centimeter cubed added point of the sodium hydroxide. These two solutions that are being reacted together have got different concentrations. So a lot of people assume it's always going to be around 25 where the vertical section happens. Absolutely not. It's going to be when we've got an equal number of moles of each reagent being added together. And so here we've already determined earlier in the question, and we were actually told to prove it, that this would be when 20 centimeters cubed of the sodium hydroxide had been added. So that means here I need to have my vertical section. Now, because I've got a weak acid, strong base pH titration curve here, I'm estimating my range as 7 to 11. The mark scheme allowed from 5 to 12, so you have got some leniency there. However, it did need to be at least 3 pH units, which is 3 boxes here on the diagram. Mine gives you 4, which is good coverage. For the final pH value up here, I've got this one, which is earlier in the question, if we just go back to it, 12 point something, 12.55, just there. And that was, again, the part we calculated in B part 2. And so this was the numerical value of when the 45 centimeters cubed had been added to the solution of propanoic acid in the conical flask, that final solution pH value. Well, here it is up here in action as our plateau point that I'm going with right at the end of the pH titration curve. Next up, moving on. The student considers using 4 indicators in table 20.2 for the titration. Which indicator would be the most suitable? So we're looking here for which one of these fits best inside that vertical section of the curve. And if we have a look at the curve once again, we know our vertical section here is estimated at 7 to 11, and therefore we can make the decision that the Cresol purple is perfect for this, and our explanation is exactly as we put in the slides earlier. The pH range of the indicator matches the vertical section of the curve. There is alternative wording that's available here. Check out the actual mark scheme for that, but personally I think this is the best one to go for. You don't end up tying yourself in knots. Next up, the question takes a turn for the worst. The solution repeats the experiment starting with 25 centimeters cubed of 0.08. Notice that's the same concentration and volume as the previous weak acid, but now they've got HCN. Now, according to the data table right at the very start here, if we go right the way back to it, the HCN has got a lower Ka value than the propanoic acid. That means the HCN is an example of a weaker weak acid, and that's going to be used in our answer just here. The student still adds all the same amount of sodium hydroxide, however, so the strong base hasn't changed. What we need to do now is predict one similarity and one difference between the pH curve that was seen before and the pH curve we would see now if we use this weaker weak acid of hydrogen cyanide. And we need to use the information in 20.1 and your answer to be part 3, so everything we've done so far. So, similarity, I've got 2 here from the mark scheme that I think would be totally okay. We'd have the same final pH solution. And so the same, the same final solution pH. And that's because we are using 45 centimeters cubed of the same alkali, the same strong base of sodium hydroxide. And so once the acid is all gone, it's irrelevant towards the pH of the final solution. And so we are just going to be looking at that same final solution pH value here. The other similarity I quite like from the mark scheme for this was the same endpoint. Because the same concentration and volume of this alternative weak acid have been used, we're going to actually need the same amount of sodium hydroxide to react it all in the conical flask. And so the endpoint at 20 centimeters cubed would also be the same. The difference, well, the main difference I would clock here is the starting pH is actually going to be higher. Here our starting pH was based on part A in this question, which was 2.98, and that's because that was the pH of the propanoic acid solution. Now that calculation involved its Ka value. If you make the Ka value smaller because you're making the weak acid even weaker, then you're going to make that pH value, even though the solution is the same concentration as the other weak acid, you're going to make that starting pH value less acidic. And so I would expect it to be a higher starting pH value. You could even calculate that to prove a point. Finally here, we've got the solution calculates the pH of, and we've got the same concentration again, but now of a different weak acid. It's the one that has the really large Ka value. I think it's called iodic 5 acid from the table previously. The student assumes that the equilibrium concentration of that weak acid is the same as the initial concentration of the weak acid. So what that's saying is when it partially dissociates, the actual concentration of the acid in that dissociation hasn't changed because that dissociation is assumed in your specification to be a very, very, very partial dissociation. However, I've already pointed out that the larger Ka value that I've noticed for this weak acid already suggests that it's dissociating a bit more than a regular one would. Explain why the measured pH is different, therefore, here than the calculated pH. So you can see that they've actually measured the pH of the solution and it's different from the one that they calculated. Well, that's because their calculation makes that assumption that the concentration hasn't changed before and after it dissociated. That the dissociation is so slight that there's still basically the same number of that acid molecule intact in the solution. Well, the HiO3, which is the iodic 5 acid, has a large Ka value, meaning it is a stronger weak acid. Be so careful here with your vocab, please. Do not say it's a strong acid. It's just a stronger weak acid. Remember, there is a scale of strength within the weak acid category. The dissociation of the HiO3 is not negligible, and so as a result, the approximations we make in our calculation of the weak acid are not valid. To round off this tutorial, I want to talk about these two pH titration curves. Here what we're looking at is the same scenario as we were presented with before. I've got sodium hydroxide, my strong base, in a burette being added to a sample of acid in a conical flask. And I'm using the same concentration of everything here, so I'm going to make some assumptions about my start and end pH values. The difference between these two scenarios, though, is I'm using a strong acid for this one in the conical flask, and for this one, I'm using a weak acid. Now, you'll notice, of course, there is the obvious difference here that if everything is presumed as the same concentration from one scenario to the next, the starting pHs are going to be different because I've got a strong acid versus a weak acid, but the final pHs are going to be the same because I've got the strong base in excess in either scenario. The important difference I want you to focus on now isn't the starting pH value or the end or even the equivalence point. This time I want you to focus on the shape of the curve at the start of each procedure. For the strong acid, strong base, you'll notice that the pH just gradually climbs up here, we zip through the equivalence point, and then we have the alkali in excess. Job done. This one, however, the weak acid strong base, seems to have a bit of a difference to its shape. In fact, if you concentrate on the shape for a moment and think about it, if we didn't see this latter half of the curve, it would almost look like the graph would plateau, where it would reach a constant pH value. And that's because that's exactly what the solution in the conical flask is trying to do. What you've got here is a weak acid in excess, and you're added small amounts of alkali to it, And around this point here, what you've established is a buffer solution. So right in the middle of your weak acid, strong base titration, the reason for this plateau shape that almost gets formed on the pH titration curve is because you've made a buffer solution during the procedure. I don't think you would intend for that to happen. You're there to do a titration. But it's interesting that this is another way the examiner could set up the formation of a buffer in a slightly different context. Thank you so much for watching this tutorial. I really hope it has made a difference, but before you go, I do need some help. Please leave this video a like before you go because it really does help support my channel and let YouTube know I still exist. There's loads of good stuff around the screen now and links to my other video content in the description down below, so make sure you check that out before you head off. Until next time though everybody, happy revising.